Assalamualaikum dan salam sejahtera. So this time I and my group will present about CFD, which means by computational fluid dynamics. So before we start, let me introduce myself and my group member. So my name is Nur Sahira Shamini binti Junhadi, matrix number B0422100050, and my task allocation is introduce group member, introduction of our topic with related theory. So next we have Google Benton as our group leader, matrix number B0422102224, with his task allocation relate result with theory and evaluate the effect of different airflow velocities on the profile. So next we have Amirul Adib, matrix number B0422100040, with task allocation, method, simulation, inlet, outlet, boundary, machine node, and explain every step clearly what and why. Lastly, we have Muhammad Shafiq Zahiruddin, matrix number B0422100045, with task allocation, explain the problem that needs to be solved in the simulation or objective, and geometry details and dimensions. So for the introduction, computational fluid dynamics (CFD) is a specialized field that employs numerical methods and computational tools to model and analyze fluid flow behavior. At its core, CFD leverages the computational power of computers to simulate and solve fundamental fluid equations such as the Euler or Navier-Stokes equation, which describe fluid motion. By applying numerical techniques to initial data and specific boundary conditions, CFD enables a detailed representation of variables like velocity, pressure, and temperature within a system. This provides comprehensive insights into how fluids interact with specific objects or structure. The application of CFD is broad, particularly in the design and optimization of various equipment, including aircraft, automobiles, and industrial machinery. By offering a deep understanding of fluid flow, CFD assists engineers in making design improvements, enhancing efficiency, and reducing development costs through computer simulation before physical implementation. In essence, CFD grants the ability to see how fluids behave without the need for physical prototypes, expediting and refining the design process across diverse industries. So for the theory that related to this topic is a computational fluid dynamics. CFD is underpinned by a profound understanding of fundamental fluid dynamics principles and numerical methodologies. At its essence are the Navier-Stokes equation, which articulate the conservation of momentum in fluid motion, serving as the bedrock for comprehending how fluids behave. The continuity equation ensures the preservation of mass within the fluid, contributing to a holistic understanding of fluid dynamics. In grappling with the intricate nature of turbulent flow, CFD incorporates turbulence modeling technique like Reynolds average Navier-Stokes (RANS) or large eddy simulation (LES). The numerical techniques such as the finite value method (FEM) or finite element method (FEM) discretize the fluid domain, allowing for nuanced approximations of fluid properties on a discrete grid. The significance of precise boundary conditions cannot be overstated. These conditions articulate the environmental vectors at the boundaries of the simulated domain. Solver algorithms, including widely utilized methods like the simple algorithm, engage in iterative processes to solve the discretized equations. Furthermore, CFD often integrates heat transfer modeling through the energy equation, offering insights into temperature distributions within the fluid and its interaction with adjacent structures. A comprehensive understanding of these theoretical underpinnings is imperative for practitioners to adeptly harness CFD in simulating and comprehending a diverse array of fluid dynamics scenarios across various industries.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shafiq Zahiruddin bin Samin. Now I will explain the objective of CFD. Simulations in computational fluid dynamics (CFD) seek to fully understand and analyze fluid flow behavior in various systems. Depending on the study, objective, and the application, different issues are handled. CFD simulations often aim to comprehend fluid dynamics in the great detail, interpreting fluid flow patterns for the automotive and aerospace industries, researching heat transfer in thermal systems, fine-tuning combustion processes for efficiency and reduce emissions, researching multi-phase flows in the oil and gas industry, simulating biomedical flows for medical device optimization, modeling turbulence for aerodynamics applications, investigating aeroacoustics for noise study, and optimizing designs for improved performance and efficiency are some of the main goals. The choice of particular problem is determined by the objective of the study, the industry that the focus is on, and the properties of fluid dynamics. The ultimate goal is to guide design choice and improve the efficiency of fluid flow systems. Okay, I will show you how to use NCs for CFD project. Firstly, go to open the workbench and you go to file and save as firstly on the desktop or PC, and I rename it as a module and then click save. Okay, now click the fluent and click geometry, right click and click new designer modeler, and then you can show the new panel on the design modeler. Click the Z axis and sketching and click setting, grid show in 2D, snap, measure grid spacing we put 0.1 meter, minus step per measure I put 10, and then click draw rectangle on the center point. So on the V1 and H1, V1 value is 1.5 and H2 is 0.3. Next, you click the concept icon and click surface from sketches, and then you click the XY plane, sketch 1 and generate and apply. After that, you can see the plate, and now you go to file and save the project. After you save the project, now you can close the design modeler, and now you can see the geometry is done. Now go to mesh. We need to solve the mesh, so you click that mesh icon. Okay, now you can see the mesh step. This is a meshing step. Now you click the Z axis. You click the axis and you can see the plate. Okay, click the generate mesh and click the mesh. You can see grid on the surface of plate. Right click mesh, insert the face meshing and select the surface and apply. You click again mesh, insert the sizing on the top boundary, okay, and the bottom boundary. Now click apply. So the type, we choose a number of division, and number of division I put a 50, and then the left boundary we choose a 60 number of division, and bias type is a bias factor and the value is 70. Now insert again in meshing, apply the right boundary, and number of division is 60, and bias type is a bias factor and the value is 70, and you click apply. Okay, after you done, you click the generate mesh. Okay, after you generate mesh, you click the mesh, you can see the grid on the surface of plate. Okay, so you go to the model and click the surface, right click and create a name selection. So the plate name is I put the air floor and click OK, and then you go to the edge icon and you click the every boundary. Firstly, I put a bottom boundary, I right click and I rename it as a plate, and the right boundary I rename it as a outlet. In the left boundary I rename it as inlet, and the top boundary I rename it as a far field pressure. Now you can save the project again and close the meshing, and then you go to the workbench, click mesh and you update on the mesh icon, and we will wait the progress until done. Okay, now mesh and geometry has done to solve.
We click the double precision and click start. So the solver processor is the number of processor of your computer have. If your computer support more processor, add more processor to the solver processor. After the loading has complete, firstly we click check and report quality, and then go to the model, viscose, choose the lamina 1, click OK. Okay, and then go to material, click the air, we open it and change the audacity and viscosity to 0.001. Click change, close. And then go to boundary condition. For the far field, we choose the symmetry one, and inlet we double click and change the velocity magnitude to 1.5 according to our data. And our data have two velocity, 2.5 and 1.5. We choose 2.5 first, and then close. This is interior airflow. For the outlet, we choose pressure outlet. One plate is wall. And then go to solution method. We change the couple into the simple, and the dash we don't change it. Go to control. The data does not change. Monitor residual, we change the unit to 0.0001 for all. This is for the graph to be more accurate. So initialization, we choose the standard initialization, compute from inlet, and click initialize. So go to run calculation. In number of iteration 1 million, and then calculate. Click OK. Go to scale residual. So this is our graph. And then go to residual, change the unit to 7, and then click OK. Go to the run calculation, calculate. OK, and this is the more accurate one. And then save project and close. Okay. And then open the result one. Go to part CZ, contour, click OK, and then change the far field into symmetry 2, variable velocity, number of contour 50, and then click apply. So for the chart, we have to build the line first. So go to location, line, and OK to insert the line. This is our length 1.5, and then the end middle is 0.3. So click apply. So the line will be here. So go to chart, click OK. Go to x axis, change into velocity u. Y axis, go to y, and data series, click the location of line 1, and then click apply. So this is the graph, and then we export to compare the line. Click series 2 files, and then search the file that we want to compare one. Now this is the line that we compare. So in contour, the maximum velocity is 2.69, and this is the boundary layer for the velocity. The air that insert at 0, and then the velocity go until 2.6 at the top of the boundary. And then we save the project and close it. Okay, and save the project. Wait until the progress done, and thank you.
Hello everyone, I'm Pupil Vindan, son of Ramachandran, and my matrix number is B042210 Now, I'm going to explain the theoretical, particularly the analytical method for finding boundary layer thickness. So, the method that I've used here, or our group have used here, is Bessier's method. So, before moving on with the calculation, this is the geometry of the plate, where V1 is the height of it, which is 1.5 meters, and H2 is the length of it, which is 0.3 meters, and on the left, written on red color, which is the airflow velocity in meter per second. Now, in this assignment, we have two airflow velocities, which are 1.5 meter per second and also 2.5 meter per second. So, for the first part, we are starting with velocity of 1.5 meter per second, where in order to find the boundary layer thickness and etc., we have to find the Reynolds number first. So here, I've used the density, the velocity, the length of the plate, and also the viscosity of the fluid to find the Reynolds number, which are 1 for density, 1.5 for velocity, 0.3 for length, and also 0.0001 for viscosity. And the Reynolds number that we get here is 4500, which is lower than critical Reynolds number at 5 to the power of 10 to the power of 5. Now, since our Reynolds number is lower than the critical, which means the flow is laminar, so we are using the Bessier's formulas, which are specially for laminar flow. So as for boundary layer thickness, we are going to multiply 4.91 with our length, and we are going to divide it with the square root of our Reynolds number, which will give us 0.02196 meter. As for displacement thickness, we are going to multiply 1.72 with our length, which is 0.3, and we are going to divide it with square root of Reynolds number, which will give us 7.6921 times 10 to the power negative 3 meter. As for momentum thickness, we are going to multiply 0.664 with our length 0.3 meters and divide it with square root of Reynolds number, which will give us the value 2.9695 times 10 to the power negative 3 meter. As for local skin friction coefficient, we are going to divide 0.664 with the square root of Reynolds number, which is 4500, and we will get 9.8983 times 10 to the power negative 3. Finally, for wall shear stress, we are going to multiply 0.332 with our density and also our velocity square and divide it with square root of 4500, which is our Reynolds number, which we will end up with 0.0111 Pascal. Now, moving on with velocity for 2.5 meter per second. As usual, we have to start with Reynolds number, where we multiply density 1 with velocity 2.5, length of 0.3, and also divide with viscosity 0.0001, which will give us 7500, and our Reynolds number is actually lower than critical Reynolds number, therefore the flow is also laminar. So to find the boundary layer thickness, we are going to use the same formula as in previous velocity, where in this case we are going to multiply 4.91 with 0.3, but divide it with the Reynolds numbers, square root of the Reynolds number 7500, which will give us 0.017 meter. Moving on with displacement thickness, we are going to multiply 1.72 with 0.3 and divide it with the square root of 7500, which will give us the displacement thickness of 5.9583 times 10 to the power negative 3 meter. As for momentum thickness, we are going to multiply 0.664 with 0.3 and divide the product with square root of Reynolds number 7500, which will yield us 2.3 times 10 to the power negative 3 meter. For local skin friction coefficient, we are going to divide 0.664 with the square root of Reynolds number 7500, which will give us the value of 7.6672 times 10 to the power negative 3. Finally, as for wall shear stress, we are going to multiply 0.332 with the density 1 and velocity squared 2.5 and divide the product of them with square root of Reynolds number 7500, which will give us 0.0239 Pascal. So, as you can see, these are the values that we get from analytical solution, which means from calculations using Bessier's method to find all the previously mentioned criteria. Now, for the next part, I'm going to move on with explaining boundary layer. So exactly what is a boundary layer? A boundary layer is a thin layer of fluid in the immediate vicinity of a bonding surface formed by the fluid flowing along a surface. In other words, or in short, boundary layer is thin layer of flowing fluid in contact with a surface. Now moving on, I'm going to explain the effects of airflow velocity on velocity profile. So when airflow velocity is low, the velocity profile near the surface is also low, but it increases gradually when we move away from the surface. On the other hand, when airflow velocity is high, the velocity profile near the surface is also high, but it decreases when we move away from the surface. Moving on, I'm going to explain what are the effects of velocity on boundary layer thickness. So when airflow velocity is low, it actually increases the viscous force. So when viscous force dominates, it actually makes the acceleration lesser. In return, makes the boundary layer thicker. Comparing to that, when the airflow velocity is high, initial forces actually dominate rather than viscous force, and this scenario makes the acceleration higher, which in return makes the boundary layer thinner. This is because Reynolds number, as you can see, is actually affected by initial forces and also viscous forces. Therefore, when viscous forces are high, the boundary layer is thick, whereas when the initial forces are high, the boundary layer is thin. Now, to conclude, velocity profile and also boundary layer thickness are affected by initial and viscous forces, as we can see clearly from the Reynolds number. Also, high airflow means the velocity profile is very steep and the boundary layer thickness is very thin due to high initial forces, whereas when the airflow velocity is low, the velocity profile is gradual compared to high airflow velocity, which is steep, and contrarily to high velocity airflow's boundary layer, low airflow's boundary layer is thicker due to high viscous forces. That's all from me. Thank you.